Okay, so this is the first session of Module 3, where we will be studying bipolar junction transistors when used as amplifiers. So this is what I want to cover for this particular, this afternoon. First, I'm going to discuss with you and improve the DC model for your bipolar junction transistor. Then we'll go into a little bit of amplifier basics. I'll just show you 1 or 2 slides on amplifier basics. And then we'll jump into the topic, the main topic for today, which is Bjt biasing. Okay, first, improve the Bjt DC model. Okay. We studied the following when we discussed Bjt basics. Okay, you have IC is equal to IS e to the VBE over V sub t. This is based on Shockley's equation. Okay, IC is proportional to IB. IB, this is just the equation. This looks like the diode equation. Since IC is proportional to IB and IB follows the diode equation, then if you just change the constant of proportionality, then you can get an expression for IC based on Shockley's relationship. Now this is okay to use for the usual values of VBE. Okay, now what if the values of VBE are small? No? If the values of VBE are small, then we have to go back to the original Shockley form. So you have IC is equal to IS e to the VBE over V sub t minus 1. So this is used with small values, okay, of VBE. Okay. Note that at VBE equal to 0, IC is equal to 0. Because at VBE equal to 0, this value becomes equal to 1, and then you have 1 minus 1 equal to 0, so IC is equal to 0. No? That is not the case here. No? At VBE equal to 0, you have a certain value of IC, although it's very small, no? Because you're going to have e to the 0, which is equal to 1. So the value of IC will be your reverse saturation current. Okay. Okay. Note also that you cannot use this expression when VBE is well, you can, but it's more accurate to use this expression when VBE is negative, no? Because here, when VBE is negative, you'll still come up with a positive IC. No? Here, when VBE is negative, then minus 1 becomes larger than this value. You come out with a negative IC. So talagang ito yung mas magandang formulang gamitin in general, no? In general. Okay, we're going to refine this formula further. Okay, the model is going to be adjusted to take into consideration what we call the early effect. No? So this one, we will adjust to take into consideration the early effect. Now, what is the early effect? Originally, we said that in active mode, your collector current is not a function of your collector to emitter voltage. We said that before. Sabi natin, dati-dati, okay, if you take a look at our plot of IC versus VCE, for a particular value of I sub B, so this becomes flat, no? So here we said that IC independent of VCE. And this is in the active mode. No? In fact, we said that IC is equal to beta times I sub B, where this is a particular I sub B. But that is not the case. In reality, if you take a look at the curve, there's going to be a slight slope. The real curve, this is the real curve. There's a slight slope. In other words, IC increases with VCE in the active mode. And this is what we call the early effect. That is what we call the early effect. Now, this is exaggerated. This is highly exaggerated. If you take a look at the real slope, the slope is going to be much smaller than this. No? I just wanted to show it this way to emphasize it. Now, why is there an early effect? What is the reason for the early effect? Okay. If you take a look at your BJT, so this, let's say this is an NPN. So this is my emitter, this is my base, and this is my collector. Okay, we know that in active mode, our energy band diagram is going to look something like this. Okay. So my emitter base junction, I'll have a depletion region. And then my collector base junction, I'll also have a depletion region. And then there's going to be more band bending in the collector base because of the large reverse bias between my collector and my base. No? On the other hand, usually the emitter base is forward bias, so my built-in potential will become smaller. Now this is what we call itong W is your effective base width. And it is within that region that there is a possibility of recombination. Remember, in an NPN, you have electrons flowing from left to right. As it crosses the base, some of it recombines, forming your base current, but most of it will go to the collector. Okay, and the recombination happens in the effective base width. Now, what will happen if I increase the collector to base reverse bias? No, if I increasing VCE will increase VCB. So this is what will happen. This is going to be the same, okay? But now, because this is more heavily reverse biased, this is going to be bigger. No? And my new W, let's say this is W prime. W prime will be smaller than W. This is because of an increase in VCB. No? If W prime is smaller than W, okay, there are less chances of recombination in the base, because recombination happens in the effective base width. If W prime is small, ang ibig sabihin nun, yung mga electrons galing dito, hindi pa nagkakaroon ng pagkakataon mag-recombine, masisweep na toward the collector. So there are less chances of recombination, and therefore alpha will increase. And if you recall, ano yung definition ng alpha? This is the percentage of emitter current that is collected at the collector. So alpha is going to increase. Therefore, I of C will increase. That's what's going to happen. I need another page, sorry. Okay. Okay, if I take a look at my family of curves, it looks something like this. Ano? Again, I'm going to exaggerate. This is exaggerated. Okay, this is IC versus VCE. If I try to extend the active region here, if I try to extend that toward the negative VCE axis, so let me do that. Okay. They will all appear to converge at one point. No, these straight lines will all appear to converge at one point. And that voltage, no, we call negative V sub A, where V sub A is what we call our early voltage. So it's after the scientists that actually studied the early effect. No? We call that the early voltage. Okay, so how do we now take into consideration the early effect in our model? So we said that I sub C is equal to I sub S e to the VBE over V sub t minus 1. We are going to multiply this by a factor which will take into consideration the increase in I sub C with respect to increasing VCE. And that factor is 1 plus VCE over V sub A. So this is now my new model, new mathematical model for an NPN BJT in active mode. Okay, note that if V sub A is large, then VCE over V sub A is small, and then we're just left with our original equation. So for large V sub A, VCE over V sub A is small. No? So that one will be very much larger than VCE over V sub A. So that this is negligible. No? That will now be negligible. And matitira na lang to, which was our original model. Now, V sub A, typically, if you take a look at products commercially available, this will be anywhere from 50 volts to about 100 volts. So actually, the value of V sub A is large. So this point extends. Kasi dito yung value of VCE, that will be only up to maybe 10, 20 volts. Pero ito, this will go 50 to 100. So actually, you can see that that the value of V sub A relative to VCE will really be large. So are there any questions? So remember this, no? Because moving forward, this is what we're going to use when we discuss the transistors and amplifier later on in this particular course, specifically when we get the small signal model of the transistor. Are there any questions? Okay, let's go to some amplifier basics. Okay, what is an amplifier, or what is amplification? Amplification is increasing the power a signal can deliver while retaining all the information in the signal. Okay. So this is our symbol for an amplifier. We use a triangle symbol. The parameter of an amplifier we call the gain. So A here is the gain. The input would typically be a weak signal, and the output would be a strengthened signal. Okay. The output must be able to drive a larger power, or must be able to produce a larger power than the input. That is the purpose of amplification. But for it to be an amplifier, all of the information at the input must be preserved at the output. So all the information at the input must be preserved at the output. If not, all info at input is preserved at output, then we say that you have a distorted output. You have what you call distortion. For example, if you have an audio amplifier, this might be an experience of some of you. You have audio amplifier and then you talk on the mic. Pag distorted yung output ng amplifier, hindi maganda yung boses nyo, basag siguro yung boses nyo, or garbled or whatever. Or if the output is distorted, the quality of the music of your audio amplifier will not be good. It will be distorted. Okay, so A is called your gain. And mathematically, your amplifier is described by the equation Y is equal to AX. Now you can describe your amplifier using its transfer characteristics. So your transfer characteristics is a plot of the output versus the input. So in this particular case, Y is your output, X is your input, and this is a typical plot. This is the typical plot of the transfer characteristics of an amplifier. So this is the linear region of your amplifier. You call this the linear region. And I think you studied this in op-amps, which follows the equation Y is equal to AX. And A must be a constant. If your system is a linear system, then A must not be a function of X or Y. It must be independent of X and Y, and it must be constant. Otherwise, you have a nonlinear system. Now, the characteristic of an amplifier is it cannot amplify an input signal indiscriminately. As you increase X, Y will not indiscriminately increase. There comes a point where you reach a positive limit on the positive side and a negative limit on the negative side. And you saw this for the op-amp. For the op-amp, the limit is dictated by your positive supply voltage and your negative supply voltage. Okay, so that is just normal in any amplifier. Okay, later on, we're going to see what these limits are for a transistor amplifier. Okay, sorry. Let me erase this. X and Y, what I'm saying here is X and Y do not have to be the same type of signal. What are the most common types of signals we encounter in EE? It's either voltage or current. So here I wrote down all the possible combinations of voltage and current for X and Y. So X and Y can both be voltages, X and Y can both be currents. X can be a current, Y can be a voltage, X can be a voltage, and Y can be a current. So when you have voltage, you call that a voltage amplifier. When you have current, you call that a current amplifier. And for these two cases, your A is dimensionless. A has no dimension, because it's volts over volts or amperes over amperes. Now, when you have a current input and voltage output, we call that a transresistance amplifier. Okay? And in a transresistance amplifier here, A has the unit ohms. Because if you multiply ohms by amperes, you get volts. And when your input is voltage and your output is current, okay, you call that a transconductance amplifier. And then in this particular case, A has the units Siemens. You multiply Siemens by voltage, you're going to get amperes. So those are some of the basic types of amplifiers. But most of what we'll encounter in this particular course would be voltage amplifiers. Okay, let's go to Bjt biasing. Okay, consider this transistor circuit. Okay, consider this transistor circuit. What will happen if I apply this voltage signal to the base of this transistor circuit? Can somebody tell me what you expect to happen at V's of O, taking into consideration the amplitude of the input signal? Can somebody tell me what do you expect will be the output at V's of O? Anyone? Can I have a brave soul try to answer the question? So I have this input signal. I apply it to the base here. What do I expect to happen at V's of O? No one? Yes, John?
Try lang po, sir.
Ano?
Try lang po. Equal po ba siya sa VCC?
Yes, you're correct, no? Very good. Equal to VCCY. Can you explain that?
Pag tinignan po yung amplitude ng input, hindi po siya enough para ma-forward bias yung base emitter. So, zero yung base current, meaning wala rin pong collector current. Kaya,
that's right. No. Very good. That's exactly the answer I was looking for, no? No? Pag tinignan mo yung amplitude nitong input signal, on the positive side, no, the positive cycle, this is what will forward bias the base emitter. Okay. It forward biases the base emitter, but it does not reach, no, the threshold voltage to make this really conduct, no? Kasi 0.1 volt lang eh, no? If this is silicon, you need at least, well, rule of thumb, mga 0.7, right? So this will not conduct on the positive side, no? Lalo na sa negative. Kasi sa negative, reverse bias natin yung base emitter junction. So in all instances, your collector current will be zero. If your collector current is zero, what is V's of O? V's of O is equal to VCC minus ICRC. If this is equal to zero, then V's of O will just be equal to VCC. So I'm glad that you tried answering that question. Now I can show what is happening, no, in relation to the transistor equation model. Now, you remember for our transistor, I of C is equal to I of S e to the VBE over V of T minus 1. No? So sabihin natin neglect early effect, which we just took up. So what does this look like? This looks like the characteristics of a diode. No? That just looks like the characteristics of a diode. So if I draw the I of C versus VBE, no? What will this look like? You have practically zero current, and then sisipa yung current natin at around 0.7 volts. Assuming that this is silicon. No? Okay. Now, what are we doing? No? Yung VI natin is equal to VBE. No? Take a look. VI is equal to VBE. This is VBE. So let me rotate this curve. Ikot ko siya. So I'm going to draw it this way. So this is my VI. I'm going to draw it this way. This is versus T. Okay? So, asan yung magiging current ko dito? Habang gumagalaw to, yung current ko nandito lang. So yung current ko laging zero. Right? Laging zero lang yung current ko. And therefore, yung output ko, laging VCC. No? That's what's going to happen. Okay. Now, my problem is, I want this signal to make my collector current change. I want this signal to make my collector current change so that I would have an output voltage that is also changing. What do I have to do to this signal para magbago yung collector current ko? Anyone? Anybody can give me an answer? Anong kailangan gawin ko sa signal na to? Yes. RD.
Try lang rin, sir. I-amplify po yung signal para mag-increase po siya sa threshold voltage po.
So lalakihan ko. Let's examine that, ha? Let's examine that. But very very good try, no? So sabihin natin lakihan ko. So gawin kong ganyan, no? So magkakaroon ngayon ako ng conduction dito, no? At this point, magkakaroon ako ng conduction. Right? Pero magkakaroon ako ng conduction only here, no? Only when my signal is here. Right? Diyan lang ako magkakaroon ng conduction, no? Kasi pag nandito yung signal ko, yung current ko, okay, aakyat yan, bababa, aakyat baba. In other words, ito yung input ko, mangyayari mag-umpisa ako dito sa IC equal to 0. Pagdating dito, nagkaroon ako ng collector current, no? Pero immediately after bababa, tapos babalik na ako dito, and then puro 0 na uli. Okay. So pag tinignan ko yung output ko, but good try, no? It's a good try. If I take a look at my output, if this is my input, so let's say dito lang ako nagko-conduct. So this is my VI. What will my VO look like? Okay, so umpisa tayo sa VCC. Okay, it's going to be equal to VCC pag wala akong collector current. Tapos dito, tumataas yung collector current ko, bababa yung output ko, no? So ganyan. No? And then magiging VCC ulit siya, tapos dito bababa ulit. Do you agree with me? Do you agree? Sino yung sumagot?
Yes po, sir. Parang may naisip naman po ako, sir, ulit. Paano,
Okay.
sir, kung magkaroon ng offset po dun sa input na signal? Bale, i-move naman po dito banda, sir.
Very, very, very good, no? I like that. That's the exact again the exact answer that I wanted. No? Para ma-amplify ko itong signal na to, ang pinakamagandang gawin is we shift it to the right. I-shift natin sa kanan, no? Because if I shift the signal to the right, para habang gumagalaw itong signal na to, gumagalaw yung point dito sa point na to, then I'm going to get a change in my collector current with a changing input signal. So ang gusto kong gawin, okay, ito yung gusto kong gawin, no? And that's exactly what you said, ano? Yun talaga, yun na eksakto yung sinabi mo. So kung ito yung characteristics ko, okay. Gusto ko nandito yung signal ko. Ito yung VI, ito yung VBE. gusto ko nandiyan yung signal ko. Kasi kung nandiyan yung signal ko, habang gumagalaw tong VI na to, okay, yung current ko naglalaro between here and here. Right? So if I take a look at I's of C, if I take a look at I's of C now, so this is my I's of C. If I take a look at I's of C, as my VI increases, my I's of C will also increase, no? Will increase. As my VI decreases, my I's of C will also decrease. So yan ang magiging I's of C ko versus T, no? And this is your VI versus T. In other words, kailangan ko ng offset. I need this offset. This offset I will call capital V, capital I. Actually, this should be small v, capital I, if we base it on our convention. So I now have VI will be equal to capital V, capital I, plus my original signal, small b, small I. So ito yung sinasabi mong offset. Okay? Ang mas tamang term sa offset, this is what we call your bias. That is what we call your bias. You have to bias the input so that it will be reproduced at the output. Kailangan ibabias natin yung input natin. Okay, by the way, if this is I's of C, what will my output look like? Yung VO. Remember, VO is equal to VCC minus IC RC. Okay. VO is equal to VCC minus RC IC. So, you start with VCC. Habang tumataas yung IC, liliit yung start at this point. Well, habang tumataas yung IC, liliit yung output natin, no? So we'll probably start here. And then habang bumababa yung I's of C natin, lalaki yung, anyway, it's going to come out something like this, no? Notice that this is the negative of this, no? Babaliktad siya. Okay. So V's of O will be 180 degrees out of phase with V's of I. Okay. So this is what we call the bias. Okay. I have a demo that I prepared for you. I have this very, very simple simulator that I have in my iPad that I often use to just illustrate things to students. So this is really just for appreciation purposes. So let me show you my simple demo. Okay. So this is the circuit that I showed you earlier. So this is just a voltage source, no? That voltage source, the amplitude, as you can see, is 100 millivolts, meaning to say it goes positive 0.1 volt and goes negative 0.1 volt. No? So the peak-to-peak value of this voltage source would be 200 millivolts or 0.2 volts. And I chose it to have a frequency of 1 kilohertz. So that's my voltage source. Wala siyang DC component. That's why you see DC is equal to 0. Then this is VCC. VCC is 5 volts. I have a 1K resistor at the collector. And then this particular transistor has a beta of 100. If you take a look, this is the beta 100. Don't mind the other parameters. Ang importante lang is itong itong beta. Beta is shown as amperes per ampere. Okay? What will happen if okay, let me show first what this signal looks like. Okay. So you can see it's 200 millivolts peak to peak. So you can read that also off. I'm sorry I don't have a pointer, no, but you can read that off the bar, that it's a 200 millivolt range signal. Okay. Now let me show you what I will observe here. Okay, because the scale changed, no, because it now has to show 5 volts. Yung 200 millivolt peak to peak, yung purple line, halos di mo na makita, no, kasi masyado na maliit yung 0.2 volts. But notice that now my output, no, which is this point, will always stay at 5 volts. It's equal to VCC. Yung earlier suggestion, anong mangyayari kung lakihan ko to? Okay, so right now it's 100 millivolts. If I make that bigger, okay, teka, no? Okay, so it's already 424 millivolts. So ang VCC ko, ganun pa rin, ano? Rather, an output ko, ganun pa rin, equal to VCC. But notice, as I increase this further, yun, no? Nagkakaroon na ng conduction kasi lumalampas na ng cut-in voltage yung... Okay? And so here you see, at the tip of the input voltage, that's when I'm approaching 0.6 volts, nagkakaroon na ng conduction. Okay? So this is 0.65 volts, may konting conduction na. Bumabagsak na yung VCC ko. And when I make that 0.7, okay, ang laki na ng conduction, right? Ang laki na ng conduction, but my output is nowhere near my input in shape. Wala, no? Obviously, if my input is my input signal, my output does not preserve the information in my input signal. Okay. Okay, so what am I going to do? Let me take this out. Let me take this out. Let me now add a voltage in series with my input. No? Oops. Ano nangyari? Sorry. Sorry, something went wrong. Sorry, sandali. Okay, let me remove this. Remove this, and then let me add a voltage in series with my input. Okay, gawin ko tong 0.7, no? Gawin ko yung 0.7. And then this is a little bit too big. Let me decrease the amplitude of my input signal, kasi right now it's 0.1 volt. I want to make it smaller. Just make it 10 millivolts or 20 millivolts peak to peak. And then this one I connect to ground. Okay, so if I take a look at this signal now, it's now offset, no? There's an offset, yung tinawag nating bias, no? So notice that the signal now goes from 700 millivolts up to 710 millivolts down to 690. So the peak-to-peak value of my signal is actually 20 millivolts, but it is offset by 0.7. Okay. Teka, liitan ko pa to, no? I think 10 millivolts is too big. Let me make it 1 millivolt. No? 1 millivolt. Yeah. So I'm going from 700 millivolts to 700, 700, yeah. Yeah, 700 millivolts to 701 millivolts, 699 millivolts. If I take a look now at this node, okay, so hindi ko na makita yung variation ng input dahil nagbago na yung scale ko. But take a look at my output. My output now is 276 millivolts peak to peak. And it is a reproduction of my input, except that it is inverted. It's a reproduction of my input, except that it is inverted. So for my 2 millivolt peak to peak input, I have a 276 millivolt peak to peak output. So what is that? No, that's a gain of that's a gain of about 138. A gain of 138. So this amplifier, this transistor with those characteristics can actually multiply my input signal by a factor of 138. Now the choice for this offset voltage that we use is important, because if I make that too large, I'm going to push my curve downward. So pag linakihan ko yan, okay. Okay, so right now it's a point. Sorry, no, let's wait for the simulation to stabilize. Okay, let me make this a little bit larger. So this was originally 0.7. Let me make it 0.75. Okay, 0.75. No. What happened? Because this is too large, because this is now too large, my transistor is always in saturation. It is now always in saturation. If you take a look at my output, it is now about 0.2. Okay, and that's just by adjusting this. No? On the other hand, if I make this smaller, okay, let's say I make that 0.6. Okay, I do not have enough voltage to make my base emitter conduct, and my transistor is always in cutoff. No? So this is very important. The value of this offset voltage is quite important. No? Okay, let's stop this for the meantime. Are there any questions? Are there any questions so far? Okay. What does my transfer characteristic look like? So this is for this pa rin, ano? So it's still this VI, VCC, RC, DO. Let me use capital, no? Capital, small v capital I and small v capital O. No? So my transfer characteristic is going to be a plot of V capital O over V capital I. We said that for small values of V capital I, so remember this is V small I plus capital V capital I, no? Where this is my bias. For small values of V capital I, my output is going to be equal to VCC. And for large values of V capital I, my output is going to be equal to VCE sat. Pag masyadong malaki yung V's of I, magsasaturate yung transistor ko. And in between the two, it's linear. Okay. Now, when V's of I is equal to 0, this is small v, small I, then V's of I will just be equal to V's of I. No? So let's say that this is that point, this is this point. No? This is capital V, capital I. Okay, itong point na to, we call this VCEQ. No? Where VCEQ, this is your quiescent collector to emitter CE voltage. Quiescent collector to emitter voltage. That is the output of your amplifier when your input signal is equal to 0. When V small I is equal to 0. Okay. So as V's of I increases, so remember this is VI, pag ganyan yan. So we start at this point. As V's of I increases, bumababa yung value ng VO ko. Right? And as V's of I decreases, tumataas yung value ng VO ko. Okay. And you have to choose a proper value of V's of I. So V's of I must be properly selected. Why? No? What if I chose too high a value of V's of I? Ano ko yung V's of I na pinili ko andito? No? Then this would be my VCEQ. Okay. Ano mangyayari, no? Habang tumataas ngayon yung Habang tumataas ngayon yung input signal ko, ang liit na lang nung pwedeng itaas niya bago umabot sa saturation. So that limits the height now of my V's of I, because if this is too high, aabot ako kaagad sa saturation. Whereas when I was here, my V's of I could be higher before I reached saturation. So obviously this point is a better quiescent point than this point, no? Okay, hindi rin maganda kung nandito yung quiescent point ko, kasi pag nandito yung quiescent point ko, habang bumababa naman yung V's of I, mas madali akong aabot sa cutoff. Right? So there will be a limit to how much my V's of I can go down before I hit cutoff. What I would like is a quiescent point, so that as my V's of I changes, I can go down the most and I can go up the most. In other words, I can play this entire line. And that's why V's of I must be properly selected. And that is the process of what we call transistor biasing. No? So this is selected. This is part of transistor biasing. You have to properly select the value of capital V, capital I. In relationship to the characteristic curves of your transistor, the characteristic curves, this is IC versus VCE. Okay. So you have, again, you have this circuit, no? V's of O, VCC, RC. So V's of O is equal to VCC minus IC, RC. Okay, if I plot this, that's called the load line. Load line. A plot of this equation is called the load line. How do I plot this here? I plot it here in the characteristic curves at IC equal to 0. So IC equal to 0 is here, no, along this axis. At IC equal to 0, VO is equal to VCC. VO, remember VCE is equal to VO. No? VO is equal to VCE. So at IC equal to 0, I have VCC. On the other hand, when VO is equal to 0, that is, I'm somewhere here. This is the line VO equal to 0. My IC is just VCC over RC. So I'll have here VCC over RC. Okay. So if I plot this line, this is now my load line. This is the load line. And my quiescent point, let's say, might be somewhere here. No? So this is now going to be VCEQ. And this is going to be my ICQ. No? So my VCEQ, my ICQ, you call this your quiescent point, or sometimes called the core operating point. So here it is shown in the characteristic curves. Here I show it in the transfer characteristics. Dito pinapakita ko sa transfer characteristics. Dito pinapakita ko sa characteristic curves. Okay. Are there any questions so far? Because I don't want to proceed unless medyo nadadigest nyo. Any questions so far? So you understand why we have to add the power supply. Okay. You understand why we have to put a power supply in series with the input signal.
Sir, may
Yes,
tanong
sir.
ako. Regarding
Yes,
po dun sa pagpili po ng value ng voltage source namin, ano po yung voltage na pipiliin namin doon? Is there a definite voltage po ba doon or ano?
Actually, ito parang rule of thumb lang for this type of circuit. Usually you try to choose a quiescent point that's in the middle of your linear section. No? Kagaya nito, no? This is my linear section. This is where my amplifier operates linearly. I usually will try to choose a quiescent point na nasa gitna nitong line na to. So that would be somewhere here. Now, if you take a look at the characteristic curves, where are you operating in the active mode? No, active mode kasi is where you're operating linearly. That's probably somewhere from here to here, no? Kasi nandito yung VC isat eh. Your VC isat is somewhere here. So you choose a quiescent point that is in the middle of where you're operating in the linear region. No? So actually, if I were to choose that point here, it probably will be somewhere here, no? Hindi dito. No? Now, if you don't have any idea, maybe a good initial guess would be at VCC over 2 for this particular case. No? Kasi ito yung VCC natin, ito halos nasa gitna. Okay? But it really depends. It really depends on the configuration of your amplifier. So parang there's no, in other words, there's no definite answer to that. It depends. Did I answer your question satisfactorily?
Yes po sir. Mag-follow up lang po ako sir na ano. So
Sige.
yung i-add po namin na voltage source po is yung value ni VCEQ. Tama po ba?
No. VCEQ, ang output, VCEQ nasa output yun eh. No? Ito yung VCEQ. Ang ina-add mo ng voltage source, itong V of I. what you add is the voltage source at the input that will make your output equal to VCEQ.
Okay po. Get, sir. Nalito lang po. Okay na po.
Yung VCEQ natin nasa output yun, ano? So yun yung parang operating point natin. Ang voltage source na i-add mo is to make your output equal to VCEQ. Basically, ang mangyayari ngayon, meron kang VI dito. Tapos ito yung VI, no? So ano yung value nito na kapag zero ito, ang output ng V sub O is VCEQ. Basically, ganun yung pagpili nito. Okay? Now, let's go to biasing schemes, no? Ang pangit doon sa sinabi ko, ang pangit dito sa biasing scheme na to. So this is a biasing scheme, no? Adding a voltage in series with your input is a biasing scheme. But what is not nice about this is I need an extra power supply. So the previous example requires a power supply to be placed in series with V sub I. No? That's not nice. This is not desirable. Why? Because we don't want our circuit to have too many power supplies. As much as possible, ang electronic circuit natin, we want to have the minimum number of power supplies. So actually, what is desirable is the bias is derived from VCC. If there's a way that this VCC can be used to provide me the bias, yun yung maganda. And there are schemes available. No? So the first scheme available, this is the simplest scheme, is what we call the fixed bias. That is the simplest scheme that is available. Okay, what is my fixed bias circuit? Let me draw it. So I have VCC. Okay, this is RC. This is VCE, which is equal to V sub O. Okay. Ito yung fixed bias circuit. Magkakabit lang ako ng resistor between VCC and my base. I will call this R bias. Okay. I call that R bias. I just connect a resistor between VCC and my base. Okay, how does this bias the transistor? Okay. So let me make an example, no? So kunwari, so let's say VCC equal to 5 volts. Okay. Let's say RC is equal to 1K. So let's put easy values here. Let's say beta is equal to 100. And then, okay, this is related to the question asked earlier, no? Anong value ng VCEQ, no? So say we want VCEQ to be equal to 2.5 volts, no? So I just said that arbitrarily, no? Kasi VCC is equal to 5 volts. Sabihin natin gusto ko lang yung VCEQ 2.5 volts. In other words, pag tinignan ko to, itong VCEQ nasa gitna lang, ano? Nasa gitna ng VCC and 0. Okay, that may not be the best bias point, but kunwari na lang for this particular case, I want VCEQ to be equal to 2.5 volts. Okay, what will be the value of ICQ? ICQ will be VCC minus VCEQ all over RC. Okay. The voltage across RC is VCC minus VCEQ. No? At VCE equal to VCEQ. You divide that by RC and I get ICQ. So this is the collector current at VCEQ. And if I compute for that, VCC is 5, VCEQ is 2.5, RC is 1K. This is just 2.5 MA. So what base current will I need to produce this collector current? So let me call that IBQ. IBQ, this is my base current at the quiescent point. This is just ICQ over beta. So that's 2.5 MA over 100. So I'm going to get 25 microamperes. 25 microamperes. Okay, when we're doing DC calculations, it's okay to just use the 0.7 approximation for VBE. No? So for DC calculations, can use VBE equal to 0.7 volts for silicon. So if this is 0.7 volts, okay, this is IBQ, right? So VCC, so IBQ is equal to VCC, VCC minus 0.7 over R bias. Okay, I know IBQ is this, so I can solve for R bias. My R bias now, I already computed it, is going to be 172 kilo ohms. So that is what I have to put here. Yan ang kailangan ilagay ko dito so that ang VCE ko will be equal to 2.5 volts. Okay, now question. How do I apply vis of I? Paano ko ngayon ipapasok yung vis of I? So let me again redraw. So this is 1K, this is 5 volts. Ito is 172K. So ito ngayon yung vis of I. This is the signal that I want to amplify. I cannot connect this directly here. No? Hindi pwede to. No? I cannot do that. Why? Because if I do that, then this is going to affect the current flowing here. Magkakaroon ako ng, ang current ko rito, using node voltage, that's 5 volts minus V of I divided by 172. No? That's going to affect the current flowing here. And besides, this is also going to be applied directly across the base emitter, which looks like an invalid circuit. No? Because this is almost always 0.7. No? So, well, yeah, if this is less than 0.7, walang problema. But if this is greater than 0.7, masisira to, no? So I cannot just connect these two. Now what do I do? Okay. I can connect V of I to the base, but I have to do it through a capacitor. your capacitor with respect to DC is an open circuit. So, yung DC current ko galing dito, okay, magpa-flow dito sa 172, walang pupunta dito because this will act as an open circuit. So all of my DC current flowing through my bias resistor here will just flow to my base here, and will be used to establish VCEQ here, no? V of O, which is equal to VCE. That will be used to establish VCEQ. Now C should be large enough so its impedance is negligible at the frequency of V sub I. Naalala niyo yung formula for impedance ng capacitor? I hope you do. X of C, 1 over 2 pi FC. That's the formula for impedance of a capacitor. Okay, so X of C, at very, very high frequencies, your capacitor is equivalent to a short circuit. No? Kasi kung malaki yung F, okay, 1 over a large number would be a small number. So meaning to say X of C is like a short circuit. So X of C is like a short circuit either at high frequencies or at high values of capacitance. So you want this to be high enough so that it looks like a short circuit to this V sub I. So what if it's a short circuit to this V sub I? Now, this V sub I can be superimposed on the DC voltage that is currently here through superposition. So if this is the case, V sub I will add to the DC voltage established by, okay, R bias through superposition. Okay, so that's how you couple your input to your amplifier. No? So you call this a coupling capacitor. Yun ang tinatawag nating coupling capacitor. But you cannot make C arbitrarily high. Because if you make C arbitrarily high, then that affects the frequency response of your entire circuit. No? You're going to study that in module 6, frequency response. Dapat yung value ng C, yung tamang-tama lang, no? Tamang-tama lang na negligible siya at the frequency of your input, pero hindi masyadong mataas kasi kung masyadong mataas yung C, yung time constant ng if you're taking 1 to 3, you know, you learn time constants. Your time constants become very, very long and your transients become too long. And your frequency response also becomes affected. So it's a balancing act determining the value of C. For the meantime, we will just assume that this C is an open circuit with respect to DC and is a short circuit with respect to V sub I. That's all you have to learn at this point in time. Are there any questions? Okay. So I'll just show you another simulation. Where did I put that? Here, no? Okay, so here, this is a 1 kilohertz 10 millivolt amplitude AC signal. 1 kilohertz 10 millivolt. I put a coupling capacitor of 1 microfarad. This establishes my bias. You call it fixed bias. It establishes my bias. This is VCC, 10 volts. This is 2K. Okay. So let's just see what the output will look like. No? So first, let me take a look at let me take a look at the input. So this is my input. So you see 10 millivolts, 0.01 volts amplitude, or 20 millivolts peak to peak. And this is how my output will look like. Again, wala yung input dahil nag-iba yung scale. So you can see that my output is being reproduced at the input is being reproduced at the output. And my peak-to-peak value of my output is 3.63 volts. The peak-to-peak value of my input is 20 millivolts, 10 millivolts positive, 10 millivolts negative. And dun sa output ko, 3.63 volts. Ganyan kalaki yung gain. That's how large the gain of this circuit is. Now, if I adjust this resistor, my curve will go up and will go down. No? So this resistor has to be set properly, because if I make this resistor too small, then this transistor is going to saturate right away. No? On the other hand, if I make this resistor too big, then this transistor is going to cut off right away. No? Magka-cut off siya at negative values of the input, magsasaturate siya at positive values of the input. And I can show that. No? I'll play around with this. If I play around with this transistor, lakihan ko, if I make it big, okay, then I tend to cut off my transistor. Okay, so kita mo yung curve ko bumababa. No? My curve is actually going down. Unfortunately, the scale is also changing, kaya hindi mo nakikita. No? On the other hand, if I make this smaller, okay, then you see now that my transistor now is reaching saturation. So kita mo nagki-clip na sa baba, that means nagsasaturate na siya. It's reaching saturation earlier. So the value of this is important. No? You have to set it. So that you get a nice reproduction of your output. Okay, no? Now, I'm going to start discussing this next meeting, but the fixed bias has weaknesses. No? Has weaknesses. It is its main weakness is sensitive to beta. Magbago lang ng konti yung value ng beta, nagbabago na yung Q point. No, it's sensitive to beta. But it is also sensitive to VBE. And unfortunately, beta and VBE are two parameters that can change very easily from transistor to transistor, even if your transistor is of the same part number. Lalo na yung beta. I can have a transistor, let's say a 2N2222. That's a very popular transistor. Typically, the beta of that is about 200, but it can go down to about 150. No? Ganun kalaki yung possible change in beta niya. The other end, yung VBE, yung cut-in voltage, no, is also differs from transistor to transistor. So that also affects our Q point. So a good bias scheme, and by the way, no, these values also change with temperature. No? Beta VBE is change with temperature. So a good bias scheme should not be sensitive to beta. No? That's the most important. Okay. So I'm going to discuss with you in the next meeting some other possible bias schemes. So I'll stop there first. Are there any questions? Any questions? So you understand the concept of biasing? Because it's a very important concept, no? The way you have to bias your input, the idea is you're biasing your input. Hindi mo pwedeng basta-basta ipasok yung input sa amplifier mo. Kailangan ibabias mo siya paakyat para dun sa, okay, so that we're here, we're operating here, and magkakaroon ka ng variation in IC. Okay, with respect to face-to-face, no, I made some announcements. Sorry, hindi niyo pala nakita because I stopped sharing already the screen. No? Hindi niyo nakita yung pinakita ko kanina. But anyway, with respect to face-to-face, let me stop recording first. Ano?